Hello, everybody. Welcome back. Today we're going to be starting a new unit, Unit 6, which is on thermochemistry. And today we're going to be working through subunit 6.1, which is on endo and exothermic processes. So let's get started. So since we're starting a new unit today, I've got our little factoid to start us off here. But as I said, we are starting Unit 6, which is on thermochemistry, and we're going to be looking at endo and exothermic processes today. And in this unit, thermochemistry is all about energy. We're going to be talking about energy all the time. And energy is defined as the capacity to do work that is traditionally more of a physics definition. It also says there to produce heat, the capacity to produce heat, and that's where chemistry talks about energy for the most part, is using the word heat. And I want us to remember the first law of thermodynamics, which is the law of conservation of energy, which is going to sound a lot like the law of conservation of mass. Energy cannot be created or destroyed, but can be converted from one form to another. And guys, there are lots of different types of energy out there. Geothermal, nuclear, chemical, kinetic, potential, electrical, solar. Many of the processes that we observe in our everyday lives are nothing more than one form of energy being converted to another. When we get to Unit 9, we're going to look at electrochemistry. We're going to look at how batteries work, and that is simply converting chemical energy to electrical energy. But the point is, the amount of energy in the universe, and I know that sounds very lofty, is constant. It's just converting one form to another. And we're going to talk primarily about two specific types of energy, one of them being potential energy. Potential energy is energy due to position or composition. Now, in your physics classes, you talk about potential energy in terms of position a lot. For example, water being held back by a dam, like if there's a man-made lake, that water has a great deal of potential energy. Or holding a bowling ball over the side of a building. That's more of a physics way to talk about potential energy. In chemistry, where we talk about potential energy is the energy stored in chemical bonds. So a great example would be saturated fat. Okay, these are molecules with long carbon chains. They get a lot of bad press in the nutritional news because it's not good for our bodies particularly. But in terms of energy, saturated fat just means a molecule that is storing a great deal of energy in its bonds. So that's where we're going to talk about potential energy in chemistry, is the energy stored in bonds. We've talked about kinetic energy before. It's, of course, the energy due to the motion of an object. We talk about kinetic energy in terms of temperature, because temperature is a measure of the average kinetic energy. We've seen this formula before, which relates mass and velocity of a particle to its kinetic energy. We'll talk about kinetic energy more in terms of its connection to temperature. One thing before we go any further, we need to make sure that you all understand the difference between these two words, temperature versus heat. And again, we've talked about temperature. Okay, temperature is a reflection of motion, okay, of a sample of gas or liquid or solid, whatever. It's related to the kinetic energy. We are going to pull this into a more thermochemistry setting because we're going to see processes where there is a change in temperature, and that indicates that something about the energy is changing. And we're going to talk about the word heat a lot in this unit. Heat and temperature are not the same thing. Heat is a transfer of energy, a flow of energy between two objects, usually because they have a temperature difference. Here's a classic example to illustrate this. Right now, wherever you are sitting, put your hand on something that is made of metal, okay? Like a doorknob, for example. Most doorknobs are made of metal. The doorknob will feel cold to your hand. Now, is that because the doorknob is actually cold? No. The doorknob is at room temperature. But our body temperature is higher than room temperature, so when we touch something metal, for example, like a doorknob, it will feel cold to our hands because we, being the hotter object, energy, heat, is leaving our hand and flowing into the doorknob. There's a flow of energy from the hotter object to the cooler object, and that's always the direction that energy flows, is from hotter to cooler. Okay, so temperature is a measure of the motion of a system of some sort. Heat is a flow of energy. It's important that you recognize that difference. Two other terms that we're going to hear a lot in this unit are system versus surroundings. Anytime I use the word system, what I mean is whatever we're focusing our attention on. Maybe that's a chemical reaction. Maybe that is a substance going through a phase change. Whatever we're focusing our attention on, that is the system. Everything else is considered the surroundings. And I want you to write this down. There's two things that it's really important that you all understand are part of the surroundings. The first thing is we, you, me, we are part of the surroundings. We are observers of the system. So we are part of the surroundings. The other thing that comes up a lot in thermochemistry questions is any kind of thermometer is a part of the surroundings. Okay, a thermometer is used to measure temperature, but temperature and a thermometer are part of what's going on with the surroundings, not the system. And I'll explain more in a minute, a context for that. When you put system and surroundings together, that altogether creates the universe. So let's get into the heart of this subunit. Endothermic versus exothermic processes. Okay, so anytime we see a temperature change, okay, of some sort, that means that there is a transfer of heat of some kind, okay, and it's either going to be an endo or an exothermic processes. So we're going to see heat exchange happening when we're heating or cooling a substance down. We're going to see it in phase changes, melting, boiling, freezing. We're going to see it sometimes when we are dissolving a solute in some sort of solvent. And of course, we're going to see it in chemical reactions as well. So let's make sure we know the basic definitions for exo and endothermic. Exothermic processes mean that heat, energy, is flowing out of the systems. Exo, exit, out of. Where is the heat going? The heat is flowing from the system to the surroundings. Sometimes you'll see the words released. Heat is released, or energy is freed. That's another word you might see. But the point is, exothermic, heat is leaving the system and going to the surroundings, whereas endothermic is the opposite. Heat is flowing into the system. Now, where is that heat coming from? It must be coming from the surroundings. Endothermic, you'll see words like heat is required or absorbed. Those are all words that indicate endothermic, heat flowing from the surroundings into the system. So let's focus on exothermic specifically. Anytime an object is simply cooling down, okay, you leave your cup of hot coffee out on the counter for an hour, it's going to cool down. Heat is leaving your cup of coffee. That's an exothermic process. Some of the phase changes are exothermic, okay? For example, freezing, going from liquid state to solid state. Heat is being removed. Energy is leaving the liquid and creating a solid. Some other exothermic processes, condensation, deposition. These are all examples where heat is leaving the system and flowing into the surroundings. Now, of course, some chemical reactions are exothermic. How would we know that? Because they will feel hot to our hands. Remember, guys, we are part of the surroundings. So is a thermometer. So if you have a thermometer down in a beaker where a chemical reaction is going on and the temperature is going up on that thermometer, that's indicating an exothermic reaction. Heat is leaving the system and flowing into the surroundings. That's us. That's the thermometer. Okay? Same thing if sometimes when you dissolve a solute in a solvent, it might feel hot to your hand. Same thing. We are part of the surroundings. So if something feels hot to our hands, when there's a reaction going on, that indicates heat is leaving the system and flowing into the surroundings. That's us. Now, on a more microscopic level, it's important that you understand why heat is leaving. Anytime you have an exothermic process going on, typically what is happening is some kind of bond or attractive force is forming. And there's a phrase that I'm going to use a lot, free to form. Energy is released or freed when some sort of connection is formed. And let me go back to the previous slide. For example, look at the first phase change, freezing. When something goes from liquid state to solid state, think about that. Intermolecular forces are being formed. Okay? Condensation, gas to liquid. Intermolecular forces are being created. So energy is freed. In terms of a chemical reaction, if it's exothermic, that indicates that the energy released when bonds were formed in that reaction must be greater in magnitude than the energy absorbed when bonds were broken. So that's why it must feel hot. But in general, guys, exothermic processes involve the forming of some sort of bond or attractive force. And this is getting a little bit ahead of myself into a little sneak preview into later subunits. You're going to see this symbol delta H a lot. H stands for heat. So the change in heat for an exothermic process will be a negative number. When we get into the math of thermochemistry in upcoming subunits, we're going to talk about why that is, but just know this for now. Exothermic processes have negative changes in heat. Let's talk endo. So if you heat an object, you take leftover chicken from dinner last night, you throw it in the microwave and you heat it up, that chicken has absorbed heat from the microwave. That's an endothermic process. Heat is absorbed. Phase changes that are endothermic, Melting, for example, solid to liquid. Heat is required, absorbed to melt a solid. Vaporization, sublimation, these are all other examples of processes that require heat. In terms of chemical reactions, it's going to be the opposite of exo, and sometimes my students have a little bit of a hard time wrapping their brains around. Why would this feel cold? Remember, endothermic means heat is absorbed by the system. Well, where is the heat coming from? The surroundings. Remember, guys, we are part of the surroundings. So if we are losing heat, whatever we're touching is going to feel cold. And sometimes that's hard to wrap your brain around. Just keep telling yourself that you are part of the surroundings. So what does this mean on a microscopic scale? If exothermic meant bonds or forces are being formed, endo is the opposite. Endothermic processes involve some sort of bond or attractive force being broken. And here's the phrase: it takes to break. It takes energy to break a connection. And if you go back and look at some of these processes, particularly the phase changes, think about it. Melting. You are breaking intermolecular forces. That requires energy. Energy will be absorbed. A chemical reaction that's endo must mean that the heat required to break the bonds in that reaction is greater in magnitude than the heat released by bonds being formed. Okay. And this is for future reference, but the changes in heat for endothermic processes will be a positive value. Again, we'll talk later about why is it positive. We'll get to that. So let's look at an example multiple choice question. It says, which statement provides the best answer and justification for the energetics of these steps? So let's look at the answer choices and we'll see if we can eliminate. Letter A says, process 1 is endothermic because energy is released when the attractions between sodium atoms are broken. So let's look at process 1. Process 1 shows sublimation, going from solid directly to gas, and that is an endothermic process. So this first part of the question sounds good. Because energy is released, no. Endothermic means energy is absorbed or required, so I can eliminate answer choice A. That's out. Letter B, process 2 is exothermic because sodium has a low electronegativity. Let's look at process 2. Process 2, let's think about what's going on here. An electron is being separated from an atom of sodium. Is that something being formed or something being broken? And I'm hoping you're answering that that is something that is being broken. We're taking that electron away. That is something that requires energy. It takes to break. So in answer choice B, that word I know is stopping me right away. Okay, process 2 is going to be endothermic, so I don't even need to worry about the rest of it. Okay, process 3. Letter C, process 3 is endothermic because energy is required to break the bond. In process 3, let's look at what's happening. It looks like 2 bonded fluorine atoms are being split apart into their 2 separate atoms. Takes to break, that is endothermic. Okay, so that sounds good. And then it says because energy is required to break the bond. So letter C sounds pretty good, but I'm going to keep reading. Let's check out letter D. Process 4 is exothermic because fluorine has a high electronegativity. Let's look at process 4, which is kind of the opposite of process 2. We're putting an electron back. We're putting an electron into an atom of fluorine. So we're forming a connection. So letter D says process is exothermic. Okay, so that sounds good because we are forming something. But then it says because fluorine has a high electronegativity, and actually this is not the right word. And you might think so, but remember guys, electronegativity means an atom's ability to attract shared electrons towards itself, meaning an atom's ability to attract electrons that are already in a bond with another atom. This fluorine is by itself. It's just fluorine atom. This is not electronegativity. The word that should be used is electron affinity. Okay, and we talked about that in a previous unit. So process D almost got it right, but not quite. So letter C is my answer. That's a great example of a multiple choice scenario with endo versus exo. Okay, let's look at a free response question. I'm going to read it to you, and then I want you to pause your video and see if you can answer it. It says, when urea is dissolved in water, a decrease in temperature is measured. Okay, think about that for a second. A student makes the following conclusion. Do you agree or disagree with the student's conclusion? So here's the student's conclusion. A decrease in temperature indicates the system is losing heat, suggesting that the dissolving process is exothermic as heat is released when urea hydrogen bonds with water. So I want you to pause the video and see if you can answer this one. All right, let's talk it through. First of all, one of these do you agree with the statement questions, that's a really common thing on the AP exam, and one of the things that I see a lot with my own students is they give these beautiful explanations, but they don't actually answer the question, do you agree or disagree? So make sure that you actually say whether you agree or disagree. I'm hoping that you all said that you disagree with the student's conclusion. Okay, so that's like 1 point on the AP exam. Then you have to go on and sort of justify your answer there. So let's think about it. We observed a decrease in temperature for this process, this dissolving process. That indicates an endothermic process. Okay, so this statement in the student's conclusion says the decrease in temperature indicates that the system is losing heat. That is incorrect. A decrease in temperature indicates an endothermic process where the system is in fact gaining heat. Again, where is that heat coming from? It is coming from the surroundings. And that also takes care of their next statement, suggesting that the dissolving process is exothermic. That's not right. We know that that is endothermic. Now, that's not all that you would need to say. At the end of the statement, the student's conclusion, this person says, heat is released when urea hydrogen bonds with water. And guys, I want you to go back and think, what are the processes going on when something dissolves in a solvent? Okay, so let's think about it. It's actually a 3-step process. Remember first that the solute particles have to be pulled apart. That is an endothermic process. Energy is absorbed. It takes to break. The second step when you're making a solution is that the solvent particles have to be pulled apart from each other as well. Also endothermic, because we're breaking some intermolecular forces. The third step is the interaction between solute and solvent. And the student's statement says heat is released when urea, the solute, hydrogen bonds with water. That's forming a connection. That's that third step in the solution process. And that is exothermic. However, so look at what I've written here. It says, although energy is released when urea hydrogen bonds with water. That is true. Guys, we know that this process is overall endothermic because we saw a decrease in temperature. So here's what I've said. Although energy is released when the solute hydrogen bonds with the solvent, the dissolving process also involves breaking intermolecular forces among urea molecules and among water molecules. Remember, we know the overall process is endothermic. The energy required to break these attractions must be greater than the energy released when the urea hydrogen bonds with water. I know that's a lot, but that is kind of something you would need to explain as part of the student's conclusion and why it's not quite correct. So that concludes subunit 6.1. In upcoming subunits, I'm going to give you a little bit more of a visual way to understand the concept of endo versus exo, and we're going to get into a lot more of the math later on. So I hope you all have learned a little something today, and I look forward to seeing you next time.